Thanks, Sasha, for the invitation. So I would like also here to thank all my co-authors. It has been a long journey during this onset of the eruption that has started back to 2021 in the Reykjanes. And here in the background, I just show an orthophoto that we did with our drone back to May 2021. And in between two explosions, we just have the chance to see the crater, the mouth of the crater in between two explosions here. The idea of the work was really to focus on the structural aspects of rifting events. And just for some background, this is Iceland here. In red and blue, we have the motion. So it's really a divergent plate boundary with the red going toward the west at about 2 centimeters per year, and the blue here at the same amount toward the west. When you look at the deformation, you can see that it's quite well distributed along the plate boundary here. You have this big curvature here, and Reykjanes is located to the southwest. Here we see clearly also here the plate boundary motion that take place. You have this kind of big seismic and tectonic and volcanic activity that started back to 2021 that is responsible for this very localized ground deformation here. If we look at a kind of classical magmatic system, similar to what Alessandro showed before, you have this magmatic system here in black. It could be caldera. I'll just show here Aschia as an example. So it's here. And the gray part are fissure swarms. And if we just isolate the dikes and the magmatic, the caldera system of one of these magmatic system, you can see here these long tongues that are dikes and that feed these fissure swarms. And here in the red is just one locus of one eruption. So you cannot see actually all the rest of the intrusion that correspond to the feeder of this eruption. We studied. Sorry for the writing here. There's some accent missing. So this is another example of the Bardarbunga rifting event that took place in 2014, 2015, and it was a kind of very impressive eruption and a kind of more classical rifting events that occur there. If you just see down right, you have here the Bardarbunga caldera. In blue, we have the seismicity that propagates northward, and finally, if I just look at here, we have this beautiful graben shape with about 6 meters of subsidence and 4 or 5 meters of opening. And if we just do some cross-section across this optical imagery, we see this graben that has been induced by the dike injection. And so a lot of deformation. Seismicity was quite low compared to the large deformation. The largest was magnitude 4.6, and despite this very strong deformation here. So a lot of the deformation usually is seismic, and that's for a kind of more classical way to see rifting events. This is how it looks like in the field. You have a large open fractures, like graben depression that form within a few days, with a graben depression that is here. And the things change a bit from this kind of conceptual model where you have the dike opening, propagating laterally over dozens of kilometers, creating a beautiful graben. And the Reykjanes example is quite a nice example of this shift in the kind of model we can get in our minds. When I went there, I said, wow, so let's try to find a graben in the area. And I was quite disappointed back to 2021 to not see any of these clear extensional structures. So the Reykjanes Peninsula here it's a clear oblique rift zone. I just need to reduce my window, okay. And we have two main, you can see we have two main directions in the fracture, in the fault system. We have this north-oriented, north-30 orientation of different fissure swarm. To the west, we have graben structures. But you also have these north-south structures that are mostly, they are very difficult to see in the field, almost not visible. If you don't know they are there, it's easy then to bypass them. And this is mostly done by these north-south structures. And when you look at the start, so the onset of this big rifting episode that started back in February 2021, here you can see the seismicity, and a lot of earthquakes were above magnitude 5. It was about 9 events. So it's quite shaky. So we have been lucky to be there during the COVID. you have been able then to feel the strong ground motion there. So 600 events larger than magnitude 3. So it is quite unusual compared to more classical rifting episodes or events we have been studying in the past. So a lot of seismic energy release, and also with widespread ground ruptures. This I just show here the sense. It's a very oblique rift zone. Actually, it's a kind of transform, a kind of more leaky transform. You have this left lateral sense of shear, quite broad. And we have also a direction of opening, which is oriented north 104, that corresponds to the opening of almost the entire Iceland here. And we have these north-south structures that are dissecting a bit the area of deformation. And then, so 2021 started the Reykjanes eruption. That was followed with the 2 other eruptions in 2022, 2023. And the system switched toward what we see also at the present time with the eruption that started again 10 days ago north of Grindavik. And in this case, we have a clear graben structure. So that's not at all the case back to 2021 here. I just showed this. I just checked this morning again because we are studying also in our group more. We are trying to better understand the full story, and that start before February 2021, so way before also the eruption that started. This is just the seismic catalog that show back to December 2019. We have all these seismic swarms. Blue is December 2019, then in the green, January 20, and then again October, July. So before the eruption started, a lot of ground motion have been observed there, a lot of seismicity, sorry. And it's as if you have a kind of tectonic release that precedes at least 1 year or 2 years before the activity in the Reykjanes. Just to show with the pointer, so Reykjanes should be somewhere here. So a lot of ground breakage that precedes the dike intrusion in this area almost 1.5 years before that. So we know that all these fractures in the divergent plate boundary form during a rifting events, and we know that there is a kind of competition between tectonic and magmatic forces, and this example is quite new actually for what we know, at least on land. We don't know what is going on at ocean bottom, so that is at least on land we know that we have often all the morphologies are often generated by dike intrusion. And in this case, we wanted to try to look at these ground fracturations that are mostly at the start of the onset of the eruption, that were mostly driven by the tectonics. I will show you why. And the idea was to go fast in the field and try to map as fast as we can all these structures with drone data, and to look at the spatial, also temporal distribution using field observation and optical imagery, as I will show later. So very high resolution drone data. And this is interesting also for the implication, because we went there and try also to know where potential eruption can start. And we'll see that in some cases it's actually most of the case you have a lot of reactivations from these faults, normal fault, graben structures and so on, but also reactivation of along eruptive fissures. This is the area. We have Grindavik here with Mount Torbjorn here. This is the actual eruption site. But back to 2021, we have these eruptive fissures in the Reykjanes area here. All the brown area are the area recovered with the drone. And you can see that we focus on specific areas, and all the dots here represent field observations. So we are a bit pushed by the time, and the idea was really to try to get as much as we can before lava flow can cover all these ground rupture evidences. And we mapped it with this small plane, so produce orthophotos and DM at between 2 and 5 centimeters ground resolution. It's a massive work that Elizabeth had presented a few weeks ago did also. She was our pilot during this mission here. We have different zones where we see a lot of ground ruptures, and this is so we arrived there, and of course we are looking for faults, and then just by walking, it's very difficult then to find ground ruptures in the field. I don't show that here, but we use a lot of interferograms also to look at discontinuities into the interferogram to organize our field observation, field work. And thanks to INSAR, we are able to localize zones where a phase has been shifted, and you can really see precisely ground ruptures. It's difficult because most of the deformation were north-south, and we know that for INSA it's difficult to completely estimate the real ground displacement in the north-south direction. This is how it looks in the field. So we have a lot of soil, and it was, you know, that all these things also get eroded after a few months. The idea again was really to try to track back this ground rupture in the field. And all this actually that we see now are fully recovered by lava flows. So all these things are transient, so we need to go fast and to recover this data. And the surprise was that we were there by looking, we are really looking forward to find the graben structures and so on, but we saw only strike slip faultings. And that's quite interesting to see that. So here we have some right lateral shear with some kind of extensional structure here, some small pull apart. We have some push-ups also here. The only open cracks we found were very close to the eruptive fissures, so about eruptive vents, maybe 15, 20 meters far from the vents. All the rest were pure ground rupture in a shear sense. I just put here a small sketch. We find a kind of very boring north 30 oriented structures, and that align in this case along the north-south direction. You can see that you create these push-ups just by aligning different segments of strike slip, and we saw hundreds of those local uplift zone of a few dozens of centimeters high, and so this is an example here. We have two main zones, and what is interesting is that all the ground rupture we found were only related to this strike slip faulting.
You're at 11 minutes now.
Yeah, we didn't see any evidences of graben structures and so on. So that's quite surprising. So here we have some data from the drone, some mapping, some zoom here in the second part from the this is the east zone here in red. And when we zoom in, we see also some very localized structures, but this is really kind of some localized features that are a bit extensive, but most of them were really strike slip faulting. And the idea was to combine, to look at ground deformation. And we were able then to access to aerial photos back to 2019 from a Luftmindir company. And then we look at post-event with our drone data. And here I just showed these three zones we have been studying in detail for the horizontal displacement field. All the ground ruptures we observed relate to earthquakes larger than magnitude 5, 5.4. All the rest were not visible at all for this event. Here on the left, we see the red rectangle that show here on the right, we have the north-south shift. And you have a very clear north-south strike slip fault that affect the area. So blue is going south and red is going north. And if you look at a bit more in detail, you see you have these en echelon structures separated by some push-ups. Most of this then related to large magnitude earthquakes without any extension in the deformation. This is just a cross-section that shows the rate of deformation. It's about 60 centimeters of shear along these north-south structures. And another example here for the very tiny, this is Fagerasfjall. We see very clear, very clean, also a shear in the north-south motion without almost no opening in the structures. And this is just to summarize a bit what we found. We have this Fagerasfjall here. The row diagrams show all the data we covered, we analyzed in the fields, all are north 30. Some of them relate to the dike direction, but most of that are actually en echelon that are aligned in a north-south direction that show these structures. We have this orientation of the main kind of shear zone. We have then the dike intrusion on north 30. And then you have all these clear north-south structures that have been activated here. This is a shear zone with a very strong tectonic presence in this case that precedes the magmatic overpressure that then align probably to north 30 here. Just to resume, so most of the structures are oriented north 30, parallel to the dike, but all are probably mostly related to tectonic faulting. Actually, at the beginning of the crisis that is still ongoing now. And we think that all these north-south events are tectonically induced, despite the dike intrusion that have been coming a bit later. And you also see that seismicity started some years before, I think that's important to keep in mind, also to look at the long-term development of these rifting episodes, rifting events. There's a change, though, between the 2021 faulting and now what we see also in the north of Grindavik from November 2023, where a graben has been forming. It's not clear. The source changed. 2021 was a deeper source. 2023 is probably more shallow source. But still, we have a kind of transition between this tectonic faulting with a higher seismicity release. We are going now towards something that is maybe more magmatic with a lower seismicity but stronger deformation, and that relates mostly to kind of more classical dike intrusion type with graben structures and so on. We found also that most of these north-south structures were already there in the past, so we just reactivate them. It's important to note that these are quite seismogenic faults, but we cannot really see them in the landscape. You just walk, and if you don't have maps of deformation, there is no way to point them in the field. So that's important for the seismic hazard into the area. Okay, thanks. Happy to take some questions.
Thanks a lot. Amazing work. I'm sure there are questions. Maybe I start with one.
Yeah.
Would you see any kind of strike slip displacements on the dikes? Is that possible, or can you exclude that? Is there some kind of strain partitioning between these north-south directed faults and the dikes, that the north-south faults take up the shear component and the dikes the extensional component, or can the dikes also have some of this?
Obliquity, yeah. I didn't see that in the models. Maybe I didn't check all of them. Need to know that, but it's I think most of the shear occur along these north-south structures, and the dike, I mean, still a very oblique rift zone, but when you look at the orientation compared to the maximum horizontal compressive stress, is almost right. It's very well aligned at north 30. So we might have a bit, but we don't see. I'm not aware about model that shows some shear in the dike too. Yeah. Other events such as Vardar-Bunga show some stronger obliquity during the opening, but in this case, I'm not aware of. So maybe other people can answer that. Yeah.
Thanks. Tom, next, please.
Yeah. Hi, Tom.
Hi. I think it's really fascinating that you don't see these graben structures in any distance away from where the eruption fissure was. Do you have any ideas for how the extension that presumably needs to be accommodated above the dike is being sort of absorbed by the shallow part of the crust there, if there are no graben structures or normal faults?
Yeah, I feel it's much more distributed. I mean, you have extension. You see that also with dike, with interferogram. You can really see that you have some extension. It's very local, and I think that probably we should also look back a bit more than just the few months before the eruption, because you have several of these seismic swarms that occur in the past that probably also create some space for a bigger dike to come. So we should look at longer time period than to look at the cumulative deformation in the area. I think there's something to explore on this on a timeline, I should say, temporally. Yeah.
Thanks.
And then Derek.
Okay, yeah, maybe similar question. It's just more like a really good talk. Was the constraints on the timing of the strike slip faulting relative to the diking? What is that? And also, what are the focal mechanisms of these big earthquakes?
Yeah, I didn't see that. So most of the focal mechanism are pure strike slips. So we can really see that.
Okay, and the timing relative to the diking, is it like before, after, during?
They all precede the dike.
Ah.
So you can really see, if you look at the seismic energy release, you can really see that you have most of the breakage before, then silence, and then I forgot now, 20 hours later, the dike just arrived and erupted passively. Yeah.
Oh, right.
Most of the deformation and the seismicity occur before. Yeah. But not only the months before, but also probably years before. This is why it's interesting to look at that, because it's a kind of longer term, a stronger tectonic influence before the dike intrusion we have compared to more classical seismicity that usually follow or coeval to the dike. Yeah.